In this video, we will look at 6 main base functions that we will be transforming. The first of those functions is our quadratic, which has the equation f at x equals x squared. In my table of values, I chose values from -3 to 3, and our function tells us take the x coordinate and square it. And I want you to remember that all negative numbers, when they're squared, they become positive. So we get that characteristic parabolic shape. And if you remember with parabolas, we also have that significant step pattern. So from the vertex, if you move to the right one, you climb up 1. If you move to the right one, you climb up 3. You move to the right one, you climb up 5. So that 1, 3, 5 was a nice step pattern for you to remember how to graph or plot the points really quickly. But you can also just remember the key points. Now, the domain for a parabola is always x is an element of all real numbers, and the range says that y has to be greater than or equal to 0 because there is nothing in the negatives because of that vertex and everything is opening upwards. For my key points, I chose the values from -2 to 2. You can also pick the ones at -3, 9, and 3, 9, but those are enough to create that U shape. In terms of properties, these are the ones that I came up with. It's a parabola. The vertex is at 0, 0. It opens up, meaning there's a minimum of 0. And the axis of symmetry, because it is a vertical line, so it's this vertical line that cuts the parabola in half. Because it is vertical, its equation is x equals 0. Now, let's move on. Something a little more new is the square root function. And for the square root function, its equation is f at x equals the square root of x. Now you will notice that the x coordinates are slightly different, and that's just based on this new function. First of all, you cannot square root a negative number. That's why I do not have any negative x values in here. Second of all, I don't feel like square rooting numbers that aren't perfect squares. So I strategically chose my x values as nice values that are square rootable. So the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, and I skipped 2 and 3 because I don't know the square roots of them off the top of my head. Then I jumped to 9 because the square root of 9 is 3, the square root of 16 is 4, and if I wanted to continue, I would say 25 goes with 5, and so on. So when you graph these key points, you get this shape here. Now you might remember square roots for when we did the inverse. The inverse of a quadratic was a square root, and the inverse of a square root was a quadratic. So this right here is one arm of a parabola that has been inverted. So for our domain here, we know that x must be greater than or equal to 0 because we can't square root a negative. And then because we only have one arm of that parabola that was inverted, y has to be greater than or equal to 0. In order for you to have this arm and the one below it, this would have to be plus or minus the square root of x, but that is not the base function. The base function is positive square root of x. Now for my key points, I just picked the nice square rootable values. And for my properties, I mentioned you cannot square root a negative. I mentioned the inverse connection. And something important to note, there's only one side that has an arrow. So this side right here, the point that was kind of like a vertex, that 0, 0, it is an endpoint. Don't assume that it will continue forever. It does not. That's why we have these restrictions on our domain and range. All right. Base function number 3 is our rational. So we know rational numbers are fractions. So our equation is f at x equals 1 over x. You will notice in your table of values, I started from -2 and went to 2, but I included one more coordinate, and that is when x equals -1/2 and +1/2, because without it, I can't really get the shape that nicely. So for all of these, I just took the x values and did 1 divided by the x value, and I kept it in fraction form, but when I plotted the point, I thought of it in its decimal. Now, you will notice that when x equals 0, if I try to do 1 divided by 0 in my calculator, you get an error. And that becomes something characteristic on our graph. So let's take a look at the graph. Here we have something that looks like these two curves, and they just go on forever upwards and downwards, and all the way to the right and all the way to the left. And you will notice that these curves never pass the x or y axis. So what we actually have here are lines called asymptote. So we have an asymptote on the y-axis, which has the equation x equals 0, and we have an asymptote on the x-axis, and because it's a horizontal line, it has the equation y equals 0. And these asymptotes are lines that your function approaches but never touches or passes through. So if we look at our domain and range, we can see the asymptotes right there. The domain is x is an element of all real numbers, but x cannot equal 0. And that matches this vertical asymptote. And for the range, y cannot equal 0. And that matches the horizontal asymptote. Now the equation of the actual asymptotes are x equals y equals, but the restrictions, of course, are x cannot equal a certain number. And if you look at it visually, you will notice that this rational expression extends forever for your x values to the negatives and forever to the positives. But at 0, there's no value, and you can see that in the table of values as well. That's why the restriction x cannot equal 0. And same thing for the y. If you look at the actual function itself, 1 over x, there's nothing that you can divide 1 by to get 0. Okay, so that's where the restrictions come from. Visually, it's the asymptotes, but you can also think about the equation itself and the restrictions on it. Now you will notice that I did actually plot 2 extra coordinates here to help me get that shape. And that's when x equals 4, so that y would equal a quarter or 0.25. And then when x equals a quarter or 0.25, I get 4 as the y coordinate just to get that shape a little nicer. But when we do transformations or when you're graphing it, these 3 points to the right and these 3 points to the left are sufficient. And those are actually the coordinates I placed for the key points. And then in terms of properties, I mentioned the asymptote and I wrote out the vertical and horizontal asymptote the way I did on the grid as well. Okay, next is the exponential. Now the exponential equation looks like this. F at x equals 2 to the power of x. Now I want you to note that this base 2 can be anything. You can have 5 to the x, a half to the x. It can be whatever it wants to be. But what's important and what makes it exponential is the fact that the variable is up in the exponent. Now for my table of values, I picked the regular values from -2. This time I went to 3, not just 2, and I plugged it into my equation. So 2 to the power of -2, 2 to the power of 3 to get my y coordinates. And just a quick little refresher here about negative exponents. When you do 2 to the -2, if you did it using your exponent knowledge, great. If you use your calculator, let's just do a quick refresh. We can turn a negative exponent positive by taking the reciprocal of the base. So it's actually the same as 1 over 2 squared, and that's why we have 1 over 4. And same thing when x equals -1/2. Now when you plot those key points, you get this shape here. You will notice that to the right it gets larger and larger, and to the left it gets smaller and smaller, but never actually approaches 0. And the reason is, if you plug a high number in for x, the y coordinate will be very high, so that's useless. But if you plug a number that is very negative, -100, -1,000, all that's going to do is make you take the reciprocal and then you have 1 divided by a really large number, which makes it 0.00000 something. So you're never actually going to get 0. You'll get really close, but not exactly, which means we have another asymptote here. But this time it's just a horizontal one, and its equation is y equals 0. So now for our domain, it can be anything for x. So x is an element of all real numbers. But for the range, y has to be greater than 0. And I want you to be very careful here because y is greater than 0, not equal to 0 because of the asymptote. So it is not y is greater than or equal to 0 because of that asymptote. So be careful with the inequality sign that you choose. For my key points, I put everything from my table. And then I just mentioned that anything to the power of 0 is equal to 1. So regardless of what your base is, whether it's 2 to the power of x, 5 to the power of x, 10 to the power of x, the y-intercept of the base function will always be 1. because anything to the power of 0 is 1. And then I mentioned the horizontal asymptote and that little explanation as to why there's an asymptote on that x-axis. Now I do want to mention for asymptotes, whether it's exponential or in the rational functions, those asymptotes can move with transformations. And so these are just properties for the base or the parent functions. All right, let's move on to our final two, which are sinusoidal. So the first one is sine x. Now, whether you're doing sine or cos, your key values for x occur every 90 degrees. And that's because if you think about your grid and you think about a circle, your key points are every 90 degrees on the quadrants. Okay, so I chose for my x values 0, 90, 180, 270, 360. And that's not something I always want you to go to the calculator for, because after you graph these a while, you won't even have to think about it. What you need to remember is that sine will always begin at 0 and then create that wave shape going upwards. So it's going to go up to the maximum of 1, 90 degrees later. Then 90 degrees later, it goes to the midline at 180. Then it goes down to the minimum at 270 degrees. And then 90 degrees later, it does a full rotation and it's back at 0. So this continues forever and ever because it is periodic, meaning the domain is going to be x as an element of all real numbers, and the range is going to be restricted based on your max and min. And our max and mins are 1 and -1. So that's what our restrictions are going to be. In terms of properties, I listed all that periodic terminology. So this is a periodic function. The period is 360, so that's a full cycle. The amplitude is 1, and the midline is at y equals 0. And remember, for the amplitude, it's the distance from the midline to the max or min. And also the midline can also be called your central axis. Okay, and finally, our cosine function looks almost identical. My key points are, again, every 90 degrees. The only difference is that we're starting at 1, which is our maximum. So cosine will begin at 1. 90 degrees later, it's at the midline at 0. Another 90 degrees, it's at the minimum of -1. Another 90 degrees, it's at the midline. Then another 90 degrees, it's at the maximum. So the domain and range, exact same as for sine. The key points are just slightly different. And then for your properties, exact same. The period is 360, the amplitude is 1, and the midline is 0.